Good afternoon. We are going to do the notes for 7.3, Similar Polygons, which is kind of the culmination of what we've been working on in the last two sections. All right, for starters, definition of similarity. Two polygons are similar if their vertices can be paired so that corresponding angles are congruent. Number two, corresponding sides are in proportion. And in proportion means that their lengths have the same ratio. So another way to say similarity is it's drawn to scale. Drawn to scale is another way to say similar because the scale factor is shaped the same, but with a more convenient size. So, for example, if the ratio of the stem to the leaf was 4:2, in a slightly larger version, it could be 10:5, and in an even larger version, the ratio could be 20:10. In all three of these figures, the stem to leaf reduces to 2/1. So 2/1 is the scale factor, and they are indeed similar. So the symbol for similarity is like a Spanish tilde or a backwards S that's kind of flat looking. And similar figures do have certain properties. First property is reflexive property. Any polygon is similar to itself. Well, that's kind of a duh. Symmetric property of similarity says if R is similar to T, then T is similar to R. Again, pretty logical. So if triangle ABC is similar to A prime, B prime, C prime, then A prime, B prime, C prime is similar to triangle ABC. So both of these are just like equalities. So is the third property, which is your transitive property of similarity. If X is similar to Y and Y is similar to Z, then X is similar to Z. There's three parts to this one. So if ABC is similar to ABC prime and ABC prime is similar to DEF, transitive property says the first one and the last one must be similar. So triangle ABC must be similar to triangle DEF. And remember, similarity means they have the same angles, but the sides are proportional, just like our sunflowers here. These three angles are the same, but each one is a different size overall. Those are similar figures. Okay, flip the page. Similarity notation. Given regular hexagon ABCDEF is similar to regular hexagon RSTUVW. So how do you write a similarity statement? Okay, so when you write a similarity statement, you have to start with matching angles. So if A and R are matching angles, then they also have to go in order. So if we're starting with A, B, C, D, E, F, on this figure, that would be clockwise. So on the similar figure, it must also go clockwise, R, S, T, U, V, W. The order has to line up just like a congruency statement. The vertices must line up. Hexagon A, B, C, D, E, F, we say is similar to, that's how you interpret that, is similar to hexagon RST UVW. Okay, in a similarity statement, corresponding vertices must be listed in the same order. So angle A corresponds to angle R in these two drawings, which means angle A is congruent to R, which means their measurements are the same. In fact, they are both 120 degrees. So matching vertices have the same measure. All right, using the definition of similar polygons, match each angle from the first figure with the congruent corresponding angles from the second figure. So B and S corresponds. This is angle B. E and V correspond, so angle V. C and T correspond, so angle T. And the last one, W and F correspond, so angle F. If the figures are similar, corresponding vertices are at congruent angles. All right, Roman numeral 4. The scale factor of similar polygons. Okay, proportional sides, which is part of the definition of similar figures, proportional sides means that any original side length over its new corresponding side length, so old over new, will reduce to form the same fraction or ratio. Any pair of corresponding sides will form the same ratio, which is called the scale factor. So in summary, proportional sides means the scale factor is a ratio of the original length over the new length. And by ratio, we mean that it is a fraction. The proportion has to be a fraction, and it will have no units. So the scale factor will have no units because they cancel out when you create the proportion. Okay, flip the page. Let's do some practice. All right, given trapezoid XYZW, similar to trapezoid NMPQ, fill in the corresponding side lengths. Okay, so original length XY, which is the top one, over new length, which would be NM, so XY over NM, is equal to, well, if the new figure is MP, the original corresponding side would be YZ, which is equal to ZW, which is the bottom of the original, over PQ, which is the bottom of the new one. And lastly, on the original figure, WX, that ratio over NQ is the same as all the others. So all four of these ratios of original over new will give you the scale factor. Again, any original side length over the corresponding or new side length will work. So let's use XY over NM because we have numbers for those. I have XY here is 30 inches and NM is 35 inches. So I can make the ratio 30 inches over 35 inches. Of course, the inches will cancel out. So I've got 30 over 35, and this is going to reduce to the scale factor. Well, 30 is 6 times 5, so 2, 3, 5. 35 is 7 times 5. The 5s divide out, and we get 6 over 7 as the scale factor of old over new. So that's how you calculate a scale factor. Find matching sides that have numbers, stack them, and reduce. Okay, number 3, create a proportion and solve for the given lengths. Okay, so we're going to find YZ and PQ, and then we're going to find the side length of YZ. All right, so number 1, we need to find the scale factor to be able to find the missing sides. So find the scale factor and its units. So we already have the scale factor, 6 over 7. That's original over new. 6 on the top is the original value. 7 is the new one. So first thing you need to do to find the missing sides of the figures is to find the scale factor. We have it. Okay, step 2, identify the side that corresponds to YZ, which is the first one we're trying to find. On the drawings up top, side MP corresponds to YZ, and we know that the measure of MP is 17.5 inches because that's what it says on the drawing. So we've identified the side that corresponds to the one we want. Step 3. Write the scale factor on the left and write your corresponding sides as a fraction on the right. You are going to match the original figure lengths and the new figure lengths to the scale factor. Okay, so on the left, we have 6, which is the original length, and 7, which is the new length, equals YZ, which is on the original figure, and MP, which is on the new. So these two correspond, and I'm putting original over new. So filling in our numbers, my proportion is 6 over 7 equals YZ over 17.5. That is the equation you need to solve. All right, so solving the proportion, let me write it down again. 6 over 7 equals YZ over 17.5. I need the 17.5 to cancel, so I'm going to multiply by 17.5 over 1 on both sides. The 17.5's divide out. YZ is alone, and it turns out 17.5 times 6 is 105 over 7. Simplify that, you get side YZ equals 15 inches. Now, where did we get inches from? The inches came from the measurement that we had, which was the length of MP, which was on the drawing. So the units of YZ are dependent upon the units of its corresponding number. So if 17.5 was meters, YZ would be in meters. If 17.5 was in miles, YZ would be in miles. 6 over 7, the units have canceled out, so that part won't change at all. The only determination of units comes from the measurement that you pull off the drawing. All right, let's flip the page to find the second part of this question. We're going to find the length of side PQ. Okay, so once again, step 1, find the scale factor and its units. So we know that 6 over 7 is our scale factor. 6 is from the original figure. 7 is from the new figure. Okay, step 2, identify the side that corresponds to PQ in the drawing. So the new side PQ, because remember PQ is new side PQ corresponds to original side length ZW, and ZW in the drawing is 32 inches. Now that we've got the corresponding side, we're ready to write the proportion. You write the scale factor on the left and write your corresponding sides as a fraction on the right. Make sure to match the units to the scale factor. So 6 original over 7 new equals ZW, which is original, over PQ, which is the new one. So our proportion that we're going to solve is 6 over 7 equals, and ZW is 32, so 32 over PQ. That's what we're going to solve. So let's go into the solving step. 6 over 7 equals 32 over PQ. Now this time what we're trying to find is on the bottom because PQ is from the new figure, and we have to have the new part of the scale factor in the same place as the new part of the right-hand fraction. All right, to solve for PQ, we're going to do flippy step. That gives us 7 over 6 equals PQ over 32. To get rid of the 32, we're going to use the reciprocal, 32 over 1. 32 cancels out. And with lots of multiplying and reducing, the length of PQ is 112 over 3. And again, we know it is inches because ZW was 32 inches, which means the one we're finding will also be inches. Inches and inches. Okay, prime notation for similarities. Prime notation distinguishes the original figure from the new or the second figure. If A, B, C, D is the original figure, or in what they give you, it's the first one they mention, then A prime, C prime, D prime would automatically be understood as the new figure or the second figure. When you use prime notation, vertex A from the original would always correspond to vertex A prime, which means the measure of A will automatically correspond to the measure of A prime. That's how primes work. So prime notation assists in finding the scale factor because, number one, corresponding vertices are labeled with the same letter. And number two, the new figure is always the one labeled with prime vertices. Now, a prime is actually almost like a exclamation point, but more teardrop shaped. That's really what a prime looks like if you were to draw it super big. It's kind of elongated. We don't really draw it that way because it's too small. So if A is your original, the new figure would be A prime. We just make a little 1. If there was a third one in the series, it would be A double prime. If there is another one in the series, it would be A triple prime. So whichever one is on the left, you would consider original. Whichever one is on the right would be the new figure. If they don't give you primes, then you have to go by what's mentioned first in the question and what's mentioned second in the question. First is always original, second is always new. All right, flip the page. Last page, let's do another example. Given quadrilateral ABCD, similar to quadrilateral A prime, B prime, C prime, D prime. Here we are. All right, complete the sentence. Side BC, okay, this is side BC, corresponds to side B prime, C prime. Because this one has primes, you know that those two match. They correspond. Okay, find the scale factor for the similarity. Okay, so number one is to find any pair of corresponding sides that have their measures labeled on the drawing. So in the drawing, side BC is 10 centimeters, and it corresponds to side B prime, C prime, which is 6 centimeters. So we have old, we have new. So when we set up the proportion, it's always original over new. Always, always, always. So BC is original, B prime, C prime is new, and that gives us 10 centimeters over 6 centimeters, which of course the units cancel out and it reduces to 5 over 3. That's our scale factor. Okay, here's one of the types of questions you're going to have. If CD is 15 and C prime D prime is 9, prove that any ratio of corresponding side lengths will reduce to the same scale factor. So we're going to prove that everything reduces to the same scale factor, which is a way to prove they are similar. So here's the proof. Original over new, CD over C prime D prime. CD is 15 centimeters. C prime D prime is 9 centimeters. Centimeters cancel, and it reduces to 5/3. So that matches the scale factor of the other two sides given. So you're proving that the corresponding side lengths are the same scale factor. All right. I'm going to put a big star on this one because this is its own. It's not really a theorem, but it is informational. Big star. If the perimeter, we're talking all the way around, perimeter of ABCD is 100 centimeters, and the perimeter of A prime, B prime, D prime is 60 centimeters, prove that the ratio of the perimeters will also reduce to the scale factor. Right now we know that the sides do, but what about the perimeters? Okay, let's fill this in. The original perimeter of ABCD over the new perimeter of A prime, B prime, C prime, D prime. And they've given you the perimeters. So ABCD is 100 centimeters. A prime, D prime, B prime, C prime, D prime is 60 centimeters. And let's reduce that. Centimeters divide out. Tens divide out. So we end up with 10, which is 2 times 5, over 6, which is 2 times 3. And what do you know? We get the scale factor. So in other words, if you have the perimeters but not the side lengths, you can still get a scale factor off of that. And that's why this is one I wanted you to pay particular attention to. All right, that is the end of the notes. Have an excellent rest of your day.